is an introductory talk. I assume zero knowledge. So if you were comfortable with the algorithms on the previous sessions, you probably don't need this talk. Okay, so let's start. So what are we going to talk about today? Can you hear me in the back? Yeah? Okay. So first we'll start with what is reinforcement learning. We'll continue with showing some mathematical tools to work in reinforcement learning. And then we will see an overview of some algorithms for model-based and model-free reinforcement learning. So what are the goals for today? I don't expect you to get very familiar with all the state-of-the-art algorithms, but I would really like to give you the knowledge to understand the underlying reinforcement learning key ideas and also definitions and notation. So you will be able to, if you are interested on this topic, to read papers or more advanced material. Okay? So let's start. So what is reinforcement learning? So during the last days, you've learned how to solve very cool problems using supervised and unsupervised learning, problems like classification, regression. But a major component of intelligence is decision making. Okay? So imagine that you are a robot and you are playing chess. So what's the best movement you can do, the best move? So this kind of problems is what reinforcement learning tries to address. Okay, so a bit more formal definition. So reinforcement learning is the branch of machine learning relating to learning in sequential decision-making settings. So we have this learner, which we will call agent. So reinforcement learning tries to learn what to do to maximize a numeric reward signal. The agent is not told which action to take. So we don't tell the agent, you should take this action. Instead, it must discover by itself which actions are good, which actions are bad. And the key concept is that it learns like following a trial and error approach. So what this is different from what you have seen before in this school. So here there is no supervision. We only have a reward signal. The feedback is delayed. It's not instantaneous. This means that, for instance, if you are playing chess and you move your pieces, and then you win the game, you don't know which exact move gives you the win, the victory, okay? Also, in here, time really matters. It's a sequential setting. And also, agent actions affect the environment. This is like in real life. If the agent takes one action, it has consequences. Imagine a robot trying to grab an object. If the object falls, there is no object anymore. Let's see a bit the framework overview, okay? So we have here our agent, we have our environment. You can think of the environment as the real world. And the agent lives within this environment and it interacts with it. So the agent receives some information from the environment, which we'll call a state. Then the agent will take an action, and this action will influence the environment. This environment changes and also gives some reward to the agent, telling if this action was good or if this action was bad. So let's talk about some examples of reinforcement learning. What kind of problems we can address with this? So many of them. I put here some of them, such as make a humanoid walk, to manage an investment portfolio, play games, as I said before, robotic manipulation, and as you saw in the previous talk by Professor Savita Maharjan, and communications. Right. Let me put you some videos of some examples to try to motivate the study of this discipline. So here we have, what do we have? We have a humanoid. This is simulation space, and it's trying to learn how to walk. And it's actually trying, it tries a bit, it falls, tries, and after 2,000 iterations, it learned to run. We have a humanoid trying to stand. It tries and tries. And after a while, eventually, it succeeds. Right. Now I'm going to show another video. Maybe probably most of you are aware of this because it's been quite famous. This is trying to play this game, Atari game. So the agent starts to learn. At the beginning, it doesn't succeed. You know, you need to play with the ball, go through all the blocks, and try to get as maximum score as possible. So I think after 200 episodes, it starts to do something. 400 episodes, it becomes quite good, probably better than me. And then after a while, at this point, the agent finds the best strategy to win the game, which is basically trying to make a tunnel there and get all the score. That's good, isn't it? So it's pretty good, yeah? Actually, this algorithm trained with reinforcement learning got better performance than humans in many different games. And then the last example I will show is robotic manipulation. This is a very, very hard problem, especially because we have a very huge possibility of actions. So here, the hand tries to match the goal in the cube. So it will rotate the cube until it takes the goal, the same configuration as the goal. So this is a very, very hard problem. And this video is, I think it's a couple of months from OpenAI company. Okay, I hope I motivated a bit because now some maths are coming. Okay. So let's start with this slide. Don't panic. This is very simple. We're going to go through this. So the framework to describe the reinforcement learning setting, we call it Markov decision process. A Markov decision process is a tuple of states, actions, transitions, reward, and discount factor, okay? So states, we already discussed about it. Work configurations. Actions is the choices made by the agent. Transitions are, so we are in given a state and the agent takes some action which will be the next state with probability. And R is a reward function, and this gamma is a discount factor between 0 and 1. We will discuss more about this later. And this comes from this Russian mathematician, Andrei Markov, because all this framework is built in one important property. Oh, well, I'm not sure if you can see. So basically, the current state in the current frame, it describes all the previous past states. And this is assuming all the framework. So it means that the future is independent of the past given the present. So this is, if you're playing a game like the one we saw, this is straightforward because you are in the current state, it doesn't matter where you are going to act anyway in the most optimal way, okay? We will revisit all these concepts again, and now let's go to more concrete example, okay? So let's see an example of a MDP in racing. So let's say we have a car and we want to travel far. And there are 3 states, okay? So the first state is the car is cool, no problem. Second state is the car is warm, so it starts to struggle. And the third state is the car is overheated, so no car anymore. And let's define 2 actions. One is going slow, one is going fast, okay? So our state space will be cool, warm, overheated. Our action space will be slow and fast. So 3 states, 2 actions. Now let's talk about transitions, okay? Let's say that we are in the cool state, okay? And we want to go fast. So if we go fast, we will go with 0.5 probability to warm state or 0.5 probability back to cool. Same for warm. If we are warm and we go fast, we'll go certainly to overheated car and we won't have car anymore. So this is what we showed before in the previous slide. This is the transition. And now reward functions. So if we go going fast, we get double reward because we are going faster, we are going to win the race. But if we are in the warm state and we go fast, our reward is -10. So we don't have car anymore and we are going to lose the race. Any question? Everything clear? Yes, please. Yeah, I mean, it could be -infinity. This is it's just a decision you make when you make the MDP, so you need to make some choices. Basically, the reward functions are manually defined. We will talk about this the following slides. Okay, let's see another example. This is a maze. So we have our agent there, and the objective is to go from the start state to the goal state. When you go to goal state, you win. In this case, the reward will be -1 per time step. We have 4 actions: north, east, south, west. And we can define the states as the agent's location in the maze, so which grid, in which cell of the grid is it. And this is a successful trajectory. When I mean trajectory, I mean sequence of states and actions. That's a one trajectory. I will revisit this concept again and again. Another example of an MDP, this is the cleaning robot. So some people have this in their houses. So here we have the robot, we have our room, and here is some dust. So if the robot navigates and takes the dust, we give a good reward. Here there's a hole. If the robot gets into the hole, we don't have robot anymore, -1. Also, we penalize 0.01 every move. Why do we do that? Because we would like the robot to don't spend energy. We want it to go straight to the dust and not wandering around until it gets to the dust. Okay, so let's say that we have these trajectories, states, actions. We need somehow to evaluate. We need to say, is this trajectory good? Is this trajectory bad? So we are going to define the return, which is defined as follows. So the return is the total discounted reward from time step t. So we are in time step t. And following this trajectory, what will be the total discounted reward? This is the return. So we have here the discount. If we have this discount is the gamma. If this is close to 0, so we have a myopic evaluation, means that we are only querying in the short term. If we have gamma close to 1, we have far sight evaluation. We are looking into the future. Why this discount? There are many reasons. The most important one probably is mathematically convenient. And also, there is some evidence that human behavior shows some preference for immediate rewards. Okay, so let's see let's revisit this example again. So we have our agent there, start. Remember, we get a reward of -1 per time step. And the agent does the following trajectory. We assume there is no discount, so gamma equals 1. So trajectory 1. Okay, so you have seen this trajectory, okay? Let's do it again. So can someone tell me what will be the return here? Remember, we have -1 for each time step. Yeah. So it basically goes down to this state and then goes back. Almost. Here they say -23. It's -24 because there are 24 cells. So basically, what we have to do is to count the rewards every time step until we get to the end of the trajectory. And here there is no discount, so or discount is equal to 1. So it's basically the sum of every time step. Another trajectory. This is the one. This is the shortest path. So as you can see here, the return is -16. And this is the best trajectory you can have because we are going from start to goal without taking any detour. So you see, the return gives us some information about how good this is a trajectory. So the higher return, the better the trajectory. Sorry, say again?
Why do you use -1 instead of only 1 in the reward?
Because you want to maximize the reward, okay? And you want to run this trajectory in the less time possible. So if it's 1, you will have lower numbers. I mean, instead of maximizing, you will be minimizing. So it's just a convention to. We want to have assign higher values to better trajectories. It's just convention. Right. So let's talk a bit more about rewards. So rewards are just a scalar feedback signal. So this is just a number, okay? The rewards can be every time step. It can be at the end of the, let's say if you are playing chess, it can be at the end of the game. You win, you lose. In general, they are sparse, they are delayed, and they only have relative value. So this is related to what we just said, relative value. So we only care about which one is bigger, which one is lower. We don't care about what's the quantity. Let's see some examples. For instance, if we want to make a humanoid robot walk, we can give some positive reward for forward motion, some negative reward for falling over. If we are managing an investment portfolio, we can give a positive reward for each money in the bank. And if we play games, we can give a positive or negative reward for increasing or decreasing a score. Okay, this was related to the previous question. This is difficult. This is a difficult problem. Some of them are straightforward, but designing reward functions is a difficult problem and often requires domain knowledge. So when you are defining your reinforcement learning algorithms, you need to be very careful how do you define your reward. And I'm going to explain an anecdote I had like 2 months ago. So I was designing my, I'm working on robot manipulation. So my problem is I want to make a robot to grab an object, okay? So I designed it to, using my reward function as the first choice was +1 if the object, at the end of the trajectory, the object is over a certain height, -1 if the object is it fell over. So I start training my algorithm, and after 1 day, I look at the rewards, at the average reward of my agent to see how it's doing. So the reward is not very good. So it was trying to learn a bit, but most of the time the object fell over, okay? So I decided to change the reward function. And I did something I thought it was smart, and I put as a reward function the distance between the table and the object, okay? So the higher the object is, the higher reward we have. So I put this to train, and the next day, I see the results. I see just the average reward and say, oh, that's doing something. So then I see the results, and it's working much better than the previous case. So I'm very happy. But still, the object fell like 60% of the times, so not very good. So I said, let's continue to train. Let's leave it for 1 or 2 days. So 2 days later, I came to the lab. I look at the reward, and wow, this is super high. And I'm so happy. But then I look at the results, at the actual results. I put an agent to work. So it was a disaster. Anyone know what may happen there? Exactly. So the agent learned how to throw the ball or the object. So yeah, it was maximizing the reward, but it was not doing what I wanted to do. Good thing it was a simulation, so no one was injured. But I want to, so this is a difficult problem. And so you need to be careful when designing this. Okay, so let's talk about now about some major components of reinforcement learning agent. So we have what we call policy, which is a function that describes the behavior by the agent. We have the value function, which gives us some notion of how good a state and or an action are. Sorry. And then we have a model, which is the agent representation of the environment. Now I'm going to go into every of these components. So policy. A policy is just a function which, given a state, give us an action. What action should they, or what action will the agent take? This policy fully defines the behavior of the agent. It can be deterministic or stochastic. The policies depend on the current state, and they are time independent, okay? So if we can define as well optimal policy. The optimal policy is the policy that gives us the maximal rewards over a trajectory. And this is actually all that we want to learn. So this is what we hope to have at the end of our training, okay? Let's see one example. Again, in the maze example. So in here, the policy will give us, given one state, which action the agent is going to take. So after training, this is the output we get by our algorithm. So if we are in here, the policy function will say go west. Let's revisit again the robot example. Similar. Here we have a policy. So if we are here, we just want to go through. So we get to the +1 reward, okay? Here we are assuming everything is deterministic. So here we assume everything is deterministic means that, let's say we want to move, going, let's say, north, and we are going to go north. There is no problem. But imagine that you are in, this robot is cleaning the house, and there is a cat that is playing with the robot. So imagine that the robot wants to go north, but the cat just pushes, and then it goes to any of the other sides with 45% probability. So we want to go straight, but the cat doesn't allow us. So the policy will change. In here, an optimal policy will be, if we are here, we don't want to go up. Because if we want to go up, we will go, we don't want to go right. Because if we go right, we'll go with higher probability to any other state rather than here. So here I want to illustrate that the policy also depends on environment. Any question to here? Okay. So let's talk a bit more about short-term versus long-term reward. When we are let's think about an investment. Okay, you may have some. If you have your investment and you are selling let's say your stocks options. Next day you will have some money, but maybe this is not the optimal action. Maybe it's better to wait a few months, so you will get a better reward. And this is also a key concept in reinforcement learning. Sometimes we need to sacrifice a bit to get a higher reward in the end. Okay, and this notion of value to codify the goodness of a state is considering a policy running into the future is what we call value function. Okay, now let's describe what is a value function. So value function is a prediction of the future reward. It's used to evaluate if this state is good or is bad, and it's defined as follows. So it's basically, if you are into one state and you run many trajectories, what will be the average reward of all these trajectories? Meaning that if you are in one state and you have this state leads to a very high reward, this is a good state. If this leads to a very low high reward, you should probably get out of there. So let's see one example again on the same maze. So here, so the value function depends on the policy. So for the case we show that we have the policy going from there, from start to goal. So this will be just the number of time steps. Okay? Let's see another example of value function. Okay? So this is related to the video we saw at the beginning. And we have this representation of the value function. So here we have the different states visited during the trajectory. And here we have the value of the value function at that state. Okay? So let's zoom a bit because I don't think you will see anything. Can you see it? More or less, well. So this is the second frame here. So we have a small peak where we have the ball in here. So meaning that this state is a good state, will give some reward. But if you see, just right after that state, it goes step down. Why? Because probably the ball is rebounding, and we are near here, so this is a dangerous state. Yeah. In this case, yes, this is deterministic.
This is a deterministic framework. Yeah. How do I differentiate thinking about value function in deterministic versus stochastic framework? Because I'm trying to think of expectations in a deterministic framework. Is there any intuitive difference?
So basically in reinforcement learning, all we care about is expectations. So if it's deterministic, you will have a mean value. But if it's stochastic, you will just do the expectation over all the possible trajectories. So the value function is defined as just this function. So if you are in a stochastic scenario, you will need to take into account the probability distributions. But this is usually estimated over the data.
Okay, and the distribution of the expectation is over the distribution of policy pi.
Oh, policy pi, yeah. So, for instance, you have a train agent. You run your agent into the environment, and you will observe a few trajectories. And then over these trajectories, you can compute this expectation.
So going back to the example, I just want to make this concept clear. So going back to the example of robot, in a deterministic scenario
which one?
Of the robot,
This one?
Cleaning robot with cat.
Yeah.
Stochastic is because you don't know where the cat is going to be, so there is some probability that the cat will block your path. Yeah. Versus in a deterministic scenario, there is still distribution of the path, but there aren't external factors changing that trajectory. So you don't need to learn the external factors, you just need to learn.
So this is integrated into the environment. We don't make any assumptions of, so in the environment where it's the cat, the robot will try to go through that direction, and something, it doesn't know what, it will just move it to some other state, which is not the state that it wanted to go. And this is related to the transition that we defined previously. So transition inputs a state, inputs an action, and so inputs current state, action, next state, and give us a probability of actually reaching that state. Yeah? Okay, thank you. Any other question? Okay. So we were here. Okay, so now we are going to zoom in this high value of the value function. Okay, and this is just the one we saw in the video, where it already dig the tunnel and is going to get a very high return. That's why this is very high. Then let's now talk a bit about model. The model, this is related to what we just discussed. There is two things that we want to learn in a model. One is the transitions, and the other one is the rewards. The model doesn't need to be perfect. It just needs to be a representation. And we'll see one example right now. Again, going to the maze example. We can give to the agent some model that we estimate, and this is the output of the model we estimated. Is very good. So we got the grid representation give us information about the transition. So if you are in that state and you move right, you will go to the next state on the right. And sorry. Yeah, so the model is not perfect because there is some part that we didn't see. So all the part but it might be good enough to learn something. We will discuss more later about models. So let's go back to the value function. So the value function is the expected return starting at S and following the policy. And it suggests dependence on the next state. I will see it now, which is called the Bellman equation, okay? So the Bellman equation, we have it here, it's defined as this. It's quite easy to prove and it's a good exercise, so if you want to do that later. So what we have here, so we have the value function of the current state. It depends on the value function of the next state. It also has some immediate reward. And then for all possible next states, we compute the probability of actually reaching that state from S under the current policy. Okay? So we are going to continue, and we will use this equation quite a few times. Any question? Okay. Yeah.
Why does the immediate reward depend on the policy?
Sorry?
Can you just say again, why does the immediate reward depend on the policy?
Because this is actually the action that we are going to take on so the policy function, we input a state, we output an action. So, from here, we are going to say, okay, can we use this to find some optimal policy? The answer is yes. So instead of what we had here, the reward function on the policy, now we are putting a max operator in here. So we are going to take the action that gives us the highest value on this value function. Okay? It may look, this is, okay, we solved reinforcement learning, but this is not as easy, and we'll see now why. Before that, let's define another function that we will be using many, many times as well, which is called the action value function. So action value function is basically in the value function, we have the state and we have the value of the state over all the possible actions. But now we are going to define the Q function or action value function where we actually have the value function given an action. So let's say we are in certain state and we want to know how good is being in that state and taking one action, that certain action, okay? And this gives us one value. So this is the expected return starting at S and taking action A and then following the policy pi. So how good is A, this action we take in that particular state and then following the policy pi for the future states, okay? Let's see one example. So again, we are in the Atari video game. So here we have different states, okay? And this represents the action value function. So in here, so in color blue, we have the action of the move. In this purple, we have the action going up, action going down. Okay, so sorry, let me introduce the environment. This is the environment of Pong. If you're familiar with that, you just need to, this is the agent, this is the other player, and we, given the ball, we try to score a goal on the other player, okay? So, let's say that we are in this state, okay? So we are here, and the ball is here, so if we don't want to lose the game, and we need to go up, because we want to move the racket until here to bounce the ball to the other side of the game. And if you take, so this is why the action value of going up is high compared to the don't do anything or going down. Because if you go down here or you don't do anything, then you will lose because you won't reach the ball. Is that clear? Okay. And then in here, in this last state, so the ball went from here to here to here and is already scoring. So doesn't matter what you do, if you go up, down, or the move, doesn't matter because you are already winning. This is the last state. So that's why all possible actions here doesn't matter. You will win the game. Okay? Okay, let's talk a bit more about optimal policies and value functions. So remember, that's what we wanted to learn, is the optimal policy, okay? So if we have the optimal Q action value function, we can just derive a policy from that, taking the best action possible by maximizing over Q, okay? So finding the optimal action value function or the value function is equivalent to finding this optimal policy, okay? And we want to move in the direction when we are doing in the direction of the greatest value over Q or V. Let's see one example here. So we have this environment. In this environment, every move we take is a reward of -1. Unless we get to these special states, which are A and B. If we get into A, we'll get a reward of +10. And if we get to state B, we get a reward of +5. And this state teleports you to these other special states. Okay? So this is what the value function looks like in doing a random policy. It means that the agent is here and takes northwest, east, south with equal probability. So we don't learn anything. It's just random. We flip a coin and we choose where it is, and we choose an action. So you see, in here, the value is high because there is quite a chance that you will get into the special state and you will have a high reward, even if it's random. Okay? Now let's see if we actually learn our reinforcement learning and we get an optimal policy, what this value function looks like. So this is after learning our optimal policy. So here we have the optimal policy. So if you are in here, you actually want to go to A because you will get teleported to A prime and you will get a high return value. So let's compare a bit both value functions of random policy and optimal. So you see, after following optimal policy, you get values, high values for most of the states, okay? Let's go back to the slide of, so we discussed about 3 different components of reinforcement learning agent. Now we are going to use these components to categorize possible approaches, okay? So there are basically in the literature 3 different big groups of approaches. One is what I call value-based, where these methods attempt to learn the value functions or co-functions that we just described. And then once they got that, they can just choose the optimal policy from the value function, optimal value function or action value function. Then there are other methods which are called policy-based, where they don't estimate any value function, and they just try to explicitly learn this mapping function of the policy, okay? And there is a last group of methods which are called actor-critic, which are basically a hybrid of the previous 2 ones, of value-based and policy-based. Then, depending if we have the model or no, we don't have the model, we have model-based approaches or model-free approaches, okay? The model-based usually estimate the model, and then based on this model, they learn the agents. In model-free, we don't make any assumption on the model. So now we are going to see a bit more on model-based learning. So in model-based learning, the basic idea is we want to learn an approximate model based on experiences, and we want to solve for values as we assume that our estimation is good, and then we want to solve the problem. Okay? So this is the first step. We try to estimate the transitions and the rewards, looking at experience or any other way we have to estimate the model. And then once we have this, we have the full Markov decision process defined. Then we can just try to solve this using some different methods that we will see later. So, okay, let's try to do one example again. Okay? We are going to try to estimate the model here using the most basic way possible. Okay? So we have an input policy, and we put the agent here to run, and we observe this. We observe that, okay, so let me show you. So we have 4 different states. One is A, B, C, D, and E, okay? And then we put the agent there, and then we observe the outcomes. So we observe, let's say the agent is in B and goes east, C, reach state C, and then gets a reward of -1, okay? And then we do this a few times, and we got all these samples. Okay? So now I will need a bit of help of you. So we have all this data. What could be a reasonable estimation of, let's say, these values? The transitions between B and C when we apply action east. So if looking at the training data, can anyone make some guess? Give you a minute or 2 minutes. If anyone knows, just say.
Anyone willing to come in front and solve this? Yeah, give a try.
No one? Just a simple guess. If you have this.
Could you explain the question again, please?
Yes. So given all these observations.
So what is the input policy?
Okay. So we have this environment, okay, and we put an agent there to move around, okay, and then we observe some data from here. We observe some trajectories of states, like, for instance, the agent moves from B.
There is no B there.
Maybe it's the screen.
Okay.
Yeah.
Okay.
Yeah. So this is sorry. This is it's a bit blurry, but this is A, B, C, D, E. Yeah. Sorry about that. Probably in these screens you can see it better. Yeah. Sorry. So we put our agent here to just interact with the environment, and we observe, for instance, that when it's in state B, it applies action east, go east, so it moves from B to C. And then after this, it receives a reward of -1. This is the first training data we have there. So after a few interactions, we get all this data. So we would like to see from this data to try to guess a model of this MDP. Because we don't know the transitions, the transition function, we don't know the reward function. Episode 4, yeah?
C east goes to D or A? Is it north?
It goes to A.
Is it C east? It should be D, isn't it? Or?
It will be if it was deterministic, but we don't know. We want to estimate
I
this
see.
transition
So that's
function.
some probability.
Exactly, yeah. Okay, let's start with maybe one state, okay? So let's start with state B. State B is C. So in here we have two samples, I think only, no? So in episode 1 and episode 2. So the best guess is that we are in B, we apply east, and we move to C. So the best guess is that it will go 100 times from B to C when we apply B. Okay? Then let's do the next one. We are in C, we apply east, and we go to D. So in the first episode, yes, we observe this. Second episode, we observe this. Third episode, we observe this. But in fourth episode, we don't observe this. So we have that 3 over 4 times. We go from C to D when we apply east. Okay? So this will be, this is 1, this will be 0.75. Everyone agrees with that? And there for the final one, so we are in C, east, C, east. So everyone agrees with the values? So in the last one, we have, we are moving from C, so we apply, we are in C and we apply east action. So actually, you could just compute that as 1 minus 0.75 according to what we have seen so far. So this is the 0.25. And then for the, now let's try to do the rewards. So the process is exactly the same, process of thinking, but let's try to move forward. So from B to E, C, B to, we are in B and go to C, we receive a reward of -1 all the time. So we assume the reward will be -1, the reward function. This is just an estimation. We could get other samples and we could get something different, and then this will change our result. But this is what the best guess we can do. We can make with what we have. Okay? So this example is just to illustrate how you could just do this in a large scale using more advanced methods, and you will try at the end to guess T and R, and you will have your model solved. So now we have the model, so we can try to solve the Bellman equation. We have T, we have R. The problem is that this is a large system, so, and also it's nonlinear because we have a max operation, because we want to get the best action. So you can solve it, there are some techniques. We can solve it using the iterative properties of the Bellman equation. Here I show one example of how to solve this. So basically, we try to iteratively learn the best value function. Okay? And this eventually converts to optimal policy. And if you're interested, you can look at the book, because it's a bit complex. Any question? I'm not going to get more into details here. We'll see something similar later. So just, you know that you can try to estimate the model. And once you have the model, you can use it to solve the MDP, because we have all the information. Problem is that in most problems, in most of the, in real world, sometimes most of the time we don't have the model. Okay? So to summarize model-based reinforcement learning, what we saw is that you can try to learn the model using supervised learning. Also, the advantage is that you can have some notion of model certainty, but the disadvantage, and this is very important as well, is that you need to first learn a model and then estimate the value function. So you have two sources of possible mistakes or errors, okay? Now let's try to go to see a bit more on model-free reinforcement learning. So in model-free reinforcement learning, we assume that we don't have a transition model, we don't have a reward model, but we have access to the environment, okay? So we can allow the agent to interact with it, or we can also have some external training data of something we have observed if we don't have access to this environment, okay? So here we have our agent. We will try to move around. I will try to eventually learn how to get into the goal by itself, okay? So now, here we have a problem, okay? So how does the agent choose these actions, okay? So let's talk about what is called exploration versus exploitation trade-off, okay? Just think about you're about to go out for dinner, and after a full day of learning, reinforcement learning, so you're tired and you want a good meal, okay? So you have basically two options. You can go to your favorite restaurant, which you know you like it, but it may be the worst restaurant in town. You don't know. So you have the option of going to the same place, or you can have the option to explore somewhere else, and you may find something better. Okay? So exploration tries to find more information about the environment, and exploitation is, from what we know, is to exploit what we know. So if we know that this is a good restaurant, so we'll have a good dinner. But maybe if we go somewhere else, we can have a better dinner or a worse dinner, depending. So this is in reinforcement learning is like in real life. You usually have a trade-off of should the agent explore or should just continue doing what it knows. Okay. Let's see some more examples. So we already talked about the restaurant selection, but you could also see this in online banner advertisements. So are we going to show, let's say, so we have some user visiting our website. Shall we show them the most successful advert, hoping that they will click on it and we'll get some money? Or we can show a different advert. Maybe the user is not interested at all, or maybe it's exactly what he was looking for, and he will click on it. And in game playing, similar concept. We can play the move that we believe is the best, or we can try an experimental move. So the most basic action selection strategy is called epsilon greedy strategy, which means that with probability y minus epsilon, we act on the current policies, so we are just exploiting. Or with probability epsilon, we explore. Okay. Problem with this strategy is one, the agent has been learning for a while. It can just make things worse. One solution is you can just lower this probability. So when the agent has learned for a while, it will be better to lower the amount of exploring and more exploiting. Okay, and there are other solutions. I'm not going to get into details, but this is the most basic strategy. Okay. Now, with all of this, anyone has any question before we get into value-based methods? Okay, let's move on. So we are still we are going now in the model-free setup. So the goal of value-based reinforcement learning methods is to learn value of states and or state actions, and from this function you can derive the policy. Okay, this is similar to what we discussed before. So let's do another exercise it's the same environment as before. Okay, so we are going to try to estimate the value function in this environment. Okay. Again, we put our agent there. It navigates the environment, and we got, I think that they are the same one as before. Okay. So now we are trying, if you want to estimate the value function here, what can you do? The most straightforward approach will be just similar to what we did before. We'll be just counting and applying the value function equation, and then we will output the values. So anyone who wants to try? Remember that value function is defined as we are in one state and we look into the future, and what will be the reward we will get, the return we will get. Okay. In here we assume that there is no discount, so let's do the easiest one. Okay. State D. State D, we have 3 samples, which are, we are in a state D, and we exit so the episode finishes, and we get a reward of +10. Episode 2, same, +10, +10. So value function in this state will be +10. This one is easy. Okay. So any guess on value function in state B? Doing the same kind of process?
To compute the value function, it's the stage we end in or we start in.
So
for example,
it's the state we start, and then we look into the future. So we look into the next steps.
So value function for B would be looking at actions B east C, B C. Is that it? And then taking the average of those reward?
Exactly, yeah.
So -1 plus -1/2. Is that the thing? Is that the value function for
So
B?
let's calculate.
stage B?
Let's calculate the sorry again. So let's calculate the return on the first episode. We are in B. So from B we move to C with a reward of -1. After that we go from C to D, reward -1, and from D to 10, reward +10. So the total return here without discount will be 8. Okay?
I need to consider the entire thing to compute value function
Exactly.
for B.
Yes. So now we have an estimate of the value function for B of 8, but we can go to the next one and do again. Same, it's the same. So we have 8, 8. Here we don't have anything about B, so
We average those two.
average these two, so we have value function here of 8. Yes, please?
Yes, thank you.
Yes, please.
So when you're estimating it for B, why don't you have to take into account that possibly when you're at C and you want to go east, you might up in A, like in episode 4? Doesn't that change the value of being in B? Because it's not sure that you're going to be able to go straight to 10.
Yes, maybe, but we don't know that yet. I mean, we have this data.
Okay, only when you start at 1.
Yeah. This is just, we will need probably a few hundreds of episodes or thousands of episodes to get some realistic value. But we're trying to do the most, what we have, only 4 episodes. So, okay, so all of this, any guess about value function of C? So we are in state C. We have state C in all the episodes. Yeah.
+4. In episode 1, C goes to D and D goes to is the output.
Who is talking?
No.
Okay.
I can start. There is laptop. Episode 1, C goes to D and D goes to output, so it's +9. In episode 2, C, that's again the case, +9.
Yeah.
Episode 3, again the same case, so +9. We have to +27. On episode 4, there's C goes to A, then A goes to the X, so it's -11. 27 minus 11 is 16, so 16 divided by all 4 episodes is +4.
Perfect. Yeah. That's the answer. Everyone understood that? Yeah. Okay. Cool. So yeah, 8, 4, and 10. And then we could continue, but let's try to do something else. So this is...
Excuse me, I had one question.
Yeah.
So you mentioned in the model-free methods we don't have a model for reward, right?
Yeah.
So is that this exercise we just did is model-free?
This is model-free, yeah.
So what exactly is changing here compared to the previous exercise, model-based one, in terms of reward here? So we still have the rewards for individual states, but the model for the
all the
reward...
data we observe.
Yeah.
I mean, we could try here to estimate the model. We are not trying to estimate the model. We are trying to estimate the value function of the...
So in terms of the difference from the previous example, what is changing here for the rewards or the model? When you said, in the first case, you said that we have a model for the reward, while here we don't have it, right?
Yeah, here we don't have it. So the motivation of this is that when we wanted to solve the MDP, we need to solve it using... So in the equation, there are some transitions and there are some rewards. So we need, if we want to have an exact solution, we need to have some estimation of this value to derive the MDP, okay? But most of the time, this is estimating this transition and this reward is difficult, okay? Because this also giving some uncertainty into your model, and you don't want this. So instead of trying to estimate the different parameters of the model, let's say, what if we try to estimate the value function directly?
So value function here is not dependent on the transition probability, or we're not thinking about it.
It's implicitly
It's
depending.
there, but we're not saying we're estimating those probabilities of transition,
Right.
which could be a lot of estimation if
Exactly,
our
yeah.
path is bigger.
Yeah.
Here, is it in... Do we have to reach the exit or whatever the end goal is in each episode in practical... or is it that you limit
You can just
after
read
a certain
this.
number of transitions when you train?
You can just see this as when you reach these two states of D and A, I think. No, sorry. When you reach D, this is the D and A. This is the end of the
Episode?
Yeah.
But so if we have a big problem where it's not easy to get to the end goal in one episode, so do we limit it to... How do we decide where you define the episode?
In real problems, you usually define the length of the episode. It can be 10 time steps, 100 time steps.
Thank you.
So this notion of trying to estimate the value function, counting which states we visit, I call it here direct evaluation, but this can go very much in complexity and this is usually called Monte Carlo value function estimation. But this is just a very simplified version, but the general idea is exactly the same, okay? So what's good about this is it's easy to understand, it doesn't require TNR, and it eventually computes the correct average values, okay? What is bad is that it will take you a while to learn this. If in any real problem you have large number of states probably. Okay, so let's try to remember the equation we discussed previously before to estimate the. So we wanted to solve the MDP using this function, but the problem now is that we don't have T and we don't have R. Okay. So we are going to do one idea, which is we are going to take some samples, okay, from the agent interacting with the environment. And then the idea is that we are going to update our value function, taking the average of these samples, okay? So this is, this high-level idea is called temporal difference learning. And we will try to learn this value function using these samples, okay? So let's, instead of using a standard average, we're going to use what's called a running average to update the value function. So it looks like this. So our value function will be updated at every sample using this equation, okay? Now let's see. So, yes. Okay, until here, it's okay? So this is just an exponential moving average. It's a way to compute the average of a time sequence. It makes basically recent samples more important to the previous ones. And also it makes sense because initial estimates of the value function are actually wrong anyway, because we are just estimating. So this is, let's see this in an example, okay? So our agent is in state B, yeah. So we observe the transition B is C minus 2, so we move from B to C, applying action east, and we get a reward of minus 2. And then we need to, now we have one sample of this transition, and we want to update. So this is our value function right now. Our value function is 0 for all states except of 8 for D. And now we observe this, and we want to update our value function using the previous equation, define it here. Sorry, yeah, here. So let's see. Any guess? We assume again gamma equal to 1, alpha equal to 0.5. So we can compute this using that equation. So reward will be, so we are in a state, we want to update this value. So we can compute using that equation, okay? So reward will be minus 2. The value function of the next state will be, is the previous one, is this one, so it will be 0. So we have minus 2 in the sample. By the alpha will be half, yeah. And then the value function of this state will be 0. Because it's already 0 here, so the current state, okay? Someone said the solution? Oh, sorry, I had the equation here, okay. -1, okay? So now we observe another transition from C to D, east, reward -2. So we plug -2 here. This is 1. This is, sorry, is D. So we're moving from here to here. So next state is T. Value function of next state is 8. Alpha is equal to half. So this gets to 3. Everyone agrees with that? Any question? How much time left I have? No. Okay. Okay, let's move on. Okay. So let's skip a bit. We're going to, with temporal difference, we can learn the value function, estimate the value function. What's the problem of the value function? Is that it doesn't, sorry. I have like 10 minutes left, I think. Continue? I think I can finish in 10 minutes because I don't have that many slides left. Okay. Okay, so the problem with temporal difference learning is that we are estimating the value function, but that doesn't give us, it's hard to select the action because we need to evaluate for all the possible actions which one leads us to the best next state value function. So why don't we, instead of estimating value function, we just estimate the Q function? Okay, so this is what's basically doing in the Q learning algorithm. I think this algorithm was mentioned in the previous talk. So we are doing a similar idea to temporal difference learning, but right now we are trying to, instead of estimating value function, we estimate the Q function, okay? So the Q function, our samples will look like this. Instead of doing the, like before, doing the value function, will look like the reward plus the maximum, the optimal action over the Q function of the next state, okay? So you want to select the action that leads us to the best Q function, in the action that maximizes the Q value, okay? So it's very similar to what we just saw, so I'm going to skip that. So there's something important in this equation of Q learning is that it's actually taking the optimal action here. And this optimal action can come from our exploration, or it can come from any other external policy, or it can even come from one human demonstration. So we can just plug here this value, and we could get a better estimate, okay? And this is what is called off-policy learning compared to on-policy learning, where we'll, instead, in on-policy learning, we'll just get rid of this max, and we'll have just the next action will be coming from the current policy. This is called difference between on-policy and off-policy approach. So I just wanted to mention this. There is another method which does the same thing, but instead of Doing the maximum here is just following the current policy. It's called SARSA, but we're not going to get into the details in here. And then, so you remember this example about our robot. So we have different states here. And we are I'm going to show a demo of Q-learning applied to this environment, okay? So this is how it looks, the Q values, okay? So we have different states, and in every state we have, we can apply 4 different actions: north, south, west, east. And this number is the Q value for each action state pair, okay? So for each state, we have 4 different actions, okay? And then we are going to see how this evolves during training. Nope. So we see the agent is exploring, is running, and then the Q values are being updated. So let's wait until it converts. So the blue dots is the agent like moving around. So after 100 episodes, we have our Q values looking something like this. So if you're in a state, in the initial state, and you need to choose an action, you would choose the one that gives you the best Q value. So in this case, we'll be going up or north, which is the highest value in this Q state, okay? And so on. So you can see at the end, we have a very good policy, because if we select the highest Q value action state at each state, we select the best action at each state looking into the Q values, we'll have something close to the optimal policy. So going up, up, right, 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 until we get to the goal, okay? And I'm almost done. I'm going to go very quick through 2 different methods, approaches, which are the policy-based reinforcement learning. We discussed about them at the beginning. So in the previous, in the value-based methods, we saw some, we estimated some value function, and then we select the action by looking into the value function. Sorry, we select the action looking into the value function. In the policy-based methods, they directly parameterize the policy, okay? So they don't care about the value function or anything. They just they parameterize this policy function with some model, for example, a neural network, and they try to learn directly this function, okay? So at the end, policy-based reinforcement learning is an optimization problem. So we have some model, like a neural network, and we try to estimate the policy function. Okay, so for this we need to define a cost function. This cost function can be the rewards, and we can just apply our favorite machine learning method to optimize this function. Okay, so this is how it looks like. This is called policy gradient approach. Maybe you have heard of that. It's pretty popular. So we update the parameters of our method based on this cost function, which this cost function can be something related to the rewards. So imagine this is our cost function. So we like to get to doing, for instance, gradient ascent and get to the highest point into this cost function. So these policy-based methods, they have some advantages over previous methods. They usually converge. They have better convergence properties. They are very much better for high-dimensional continuous action spaces, and they have been used in the most recent, with very high success in recent papers, like the one we saw of hand manipulation. They're using policy gradients, and I think the alpha 0 from DeepMind are also using policy gradients. As a disadvantage, they DPI converts to local rather than to global optimums, and usually evaluating the policies is quite time-consuming. And just to finalize in the different methods I just described, I introduced. So a brief note on actor critic methods, where basically they are a hybrid of value-based methods and policy-based methods, where they have some critic, which is the policy evaluation, was basically estimating some value function. We can do it using a temporal difference. We can use it direct evaluation. And then for they also explicitly use a policy function, which they call actor. And this actor usually, updates the policy parameters in the direction suggested by the critic. Okay? So this is just, I did a final slide to recap about all the today's methods. And so this could be seen as the anatomy of reinforcement learning approaches, where depending on different assumptions or different methods, we have different goals. Okay, but the final goal is the same for everyone. We want to get optimal policies, but we can do it using different strategies. Okay, and then this is the last slide. So, we have seen for instance, Q-learning. We had this table with different several states, but this might not be feasible to do it in real life, because for instance, if you play Go, this game, you have 10 to 170 states. So this is, I read somewhere this is higher than the number of atoms in the universe. So if you want to put that into a lookup table, and if you do navigation problems, your state space is also continuous, so you cannot do this using tabular methods. So you will have to do some function approximation. And this function approximation is probably the reason of the success in the last few years of reinforcement learning, where they have been combining deep neural networks with reinforcement learning to solve very challenging problems. And yeah, I think that's all. So I put here some bibliography if you want to check some textbook or some more advanced reinforcement learning courses. All of them are open source. All of them are free. And even this is the best textbook. It's free, available free, so you can just download it and get some more into details if you are interested on that. And I think we are all hungry. So I'm going to finish here.
So we will take few questions, not many. Yeah.